So I apologize in advance if these videos are, not professional looking. I'm definitely not a person who likes making videos. So this is a first for me. I DJ'd for many years, so I understand, and I make music and things like that. So I kind of understand production and whatnot. But what we're gonna do here, I'm just gonna kind of go through the paper itself, part by part, and just re-surmise it and kind of explain it out. So we're going to start off with part one, which is quantum thermodynamics and the entropic origin of inertia. So the first thing is it's an introductory paragraph. I'm just going to highlight it. The topological friction arising from the movement of the particle through the vacuum is ultimately what causes the moment of inertia for everything. There's a lattice of connected six-dimensional manifolds that arose as string theory described at the breaking point of the start of everything. The framework that we go over, it unifies this concept of force with geometry. The movement of the parts ultimately dictates the inertia and how things interact with one another. We demonstrate that Einstein's field equations can be viewed as an equation of state derived from the thermodynamic relationship where gravity is the entropic force resulting from the geometric displacement. In this view, inertia is a direct viscous drag resulting from the physical movement of the particle's constituents through the vacuum medium. What this really kind of boils down to, as simple as it might sound, it's the principle of least action. So, and it's more like the principle of least topical friction, because when the matter-induced volumetric expansions of the parts that are in a location are they're stretching space in that whole six-dimensional manifold. So that is kind of feeling out into the future for its path to ultimately take. It's going to be the one it has the least friction. It's going to be the easiest path or the most direct path possible for those moments. It has the entropic action integral. This is an equation that kind of represents the geometric drag. We'll go over the math again more in detail in the future. I really want to just kind of cover all of these parts in general and see who can follow along. All right, so section 3.2, thermodynamic implications. This modification fundamentally alters the variational principle. The system does not just minimize the kinetic energy minus potential energy. It minimizes the informational cost of actually displacing space itself. The low energy limit logarithmic term, it ends up vanishing and the system recovers standard general relativity. However, as energy density increases, as is with the top quark, the entropic term dominates, forcing the system to minimize vacuum hysteresis loop. This implies inertia isn't just an intrinsic property of the particle, but rather the vacuum's resistance to having its shape rewritten. A particle accelerating through this vacuum is analogous to a body moving through a fluid. It has to perform work in order to displace the medium. The next part, it's the derivation of constants from observational anomalies. When the yield point is derived from the Higgs stability scale, the remaining mechanical constraints of the vacuum, the viscosity, the resolution, the resonance, are derived directly from high significance tensions in contemporary cosmological data. We interpret these tensions not as statistical errors, but as precise measurements of the vacuum's material properties. And what that ultimately says is that our modern science thinks that space isn't anything, that we're just coasting through boxes, so to say. But the information shows otherwise. Space is something. It has actual physical properties to it. So first thing, viscosity, the S8 tension. They kind of have already observed the universe is approximately 8.4% smoother than predicted by just general relativity alone. Based on the Planck CMB data, the structure growth is being suppressed by non-gravitational dampening force. We model this cosmic structure growth as harmonic oscillator damped by the bulk viscosity of the vacuum. The observed amplitude relates to the general relativity prediction via the exponential decay over the age of the universe. So ultimately, they've already seen the effects of not having this final term to explain space's finite capacity locality. So section 4.2 goes into the resolution, the proton radius puzzle. So there was a experiment done in regards to the proton radius that was measured via electron scattering. It has a specific size. And so they took one reading at one point for that, then they took another reading, and they were different. That being said, it was ultimately the experiment that was done itself changed the shape of the board for the measurement, which is why there was a discrepancy in the first place. In QSM, this geometric effect, the vacuum has a discrete grain size. The electron, having a large de Broglie wavelength, floats over the grain, while the heavier muon interacts more deeply on the inverse fine structure constant, which governs the stochastic interaction steps. Pardon me as well, as some of these words, I don't generally speak about them. They are bigger words. I understand the underlying effects, and I'm just getting to know them better and to speak them as well. So I don't really hang around a lot of people who know how to pronounce some of these things either, so I'm doing the best I can. Section 4.3, resonance. The Hubble tension, like I said, when you have things moving through space and you don't realize that space has properties, you're going to see a mix match of signals while your equations say, hey, it should only be this. We interpret this time delay dispersion, light traveling through the vacuum experiences group velocity lag dependent on the vacuum's quality factor. Okay, depending on what is in that location of space will depend on how light moves through it, and ultimately what we see. They see some galaxies with dark matter, they see some without. We'll get into that here later. But understanding the resonance does it help? That's what it's for the Hubble tension. It'll help resolve that and show why there's a discrepancy there. The dual viscosity framework and their scalar curvature. For section 5, a central challenge in physics is reconciling the high stiffness required to explain cosmological stability with the low drag required for local inertia, local inertial motion. We resolve this by modeling the vacuum as a superfluid of 6-dimensional manifolds. I didn't put it in there, but it's technically connected by a lattice of strings, so to say, the Higgs itself. But that being said, what we go through here is Finsler geometry. I know basic geometry, from school and everything else. Like I said, I seen when they didn't do the one more step correctly, and this was back in 2021, and I wanted to make sure that I was right before I really kind of took this thing further, because I thought I can't believe nobody's seen it before. Either way, back to the topic at hand, the Finsler geometry. It assumes that momentum space is Euclidean. That's what standard quantum field theory assumes. It's an assumption. They don't have any other real reason to think that, other than just that's how it's always been. And actually, it wasn't. There was a time long ago when they thought that space was something. They got rid of the Aether theory or whatever, and that's probably where that came from, if my memory serves correctly. But however, the anomalies, the viscous anomalies derived above, implied the vacuum has an intrinsic grain or directionality. We formally describe this using the Finsler geometry. It pretty much shows that space has a direction that it prefers. We've actually seen this in an analog in an experiment already, where a particle will have mass in one direction but not the other. Scalar velocity curve. We propose that the vacuum viscosity is not a single constant but a scalar function, dependent on the intrinsic geometry of the interaction. The Higgs is the only spin-zero scalar field that we know of. That's why. That's the Higgs was really the kind of key for all of it. So hopefully these videos will help people who need it to understand these ideas more clearly. Section 5.3 shows discrete reference frames, particle generations, generation 1, generation 2, generation 3. It all has to go back to ultimately the angle of attack of the string involved in moving the space in the first place. 5.4 shows the experimental validation, the yield point, which has been seen in experiments. That section goes through that. Section 6, covariant formulation of the vacuum viscosity. What happens here is, and I keep saying the whole paper is formatted in a we format. Apparently science, all their information that they've been kind of doing, they put we on it. They keep it somehow objective and like that. Technically, this was just me using an advanced calculator to fill in the details and make sure it was right. So, but we extended the ideal fluid approximation of general relativity to include the dissipative terms arising from the saturation of the vacuum stress energy tensor. And then we go into that on here. It kind of runs through that math. And then section 6.2, there's an actual vacuum limit. There's a top end to how much energy or matter you can put into a location before it fills up. And it goes through several stages before it gets there too. Which is ultimately what happens in a black hole. It starts out with a period, an area of extended space where things fall into it. Then space thickens up and it becomes thick like a plastic, and the geometry is moving around it at a superfluid pressured way. And then you get to its core, which is an actual object. It's got a size to it. Space right at that location is completely filled up and linked into the grain of the Higgs itself. It's unified at that point. So they're at the same angle. But section 6.3 is quantitative analysis of the vacuum expansion and rotation curves. We go through all that. It goes over the cutoff radius limits. It gives the math for that. It uses empirical validation. We used our Milky Way data that we have to do that math and show how that works out. It shows the viscosity of the expanded geometry. It predicts galactic velocity as well. And then we go into the bridge equation, which we're going to go into that all, but I'm going to make a whole video on the bridge equation. The derivation of that, it goes through using the bridge equation to go from the quantum size all the way up to our macroscopic scale. Then section 7.2, it gives you an example, the inertial wake, the top quark versus the electron. They're in different locations relative to that depth of the Higgs field when they're moving space. So the electron itself is on the top, kind of wiggling around or whatever, doing its thing in accordance with the math. And the top quark it's a type 2A/B geometric defect. So it's deeper in its overall size. It makes a cavitation into space, the Higgs itself. So we show the math for the internal ratio, the thermodynamic relation, and so that was all done using the bridge equation. Like I said, we are going to go through a whole video probably of that by itself. Section 7.4 is the experimental correlate, giant noise shot. There was an experiment that was done, and it didn't exactly fit the standard model's prediction. We used these equations in order to analyze it and found the discrepancy. And we show that here with the standard model prediction, why it failed, the experimental observation, and then the QSM prediction, which shows exactly why they saw what they saw. So section 8 is the rotational dynamics, the entropic moment of inertia. While linear inertia represents topological friction arising from a translation through the vacuum lattice, the rotational inertia presents a uniquely hydrodynamic case. It's vortex drag. Many people have seen these effects for the vortex drag and stuff, and have been trying to make unified field theories out of it from what I've seen personally for quite a while. So it's just missing part of the picture. I understand why they're seeing what they are, but that vortex drag, it actually comes into play when you're dealing with matter in space. So it goes down to the angular geometric resistance of the strings itself that are in space with these manifolds moving through them. So section 8.2 is vortex drag stability. Section 9 is engineering the vacuum. Metasurfaces and wakes. Listen, this technology that we can utilize here, it's going to have a wide range of effects. Thankfully, our level of technology is low enough where we can't exactly weaponize this stuff yet. It would end up ending badly for anyone. You can't generate enough energy per se right now to use it for some kind of weapon of mass destruction or anything like that, as far as I can tell. So we can tap into it for understanding and for energy, which is going to be critical. So section 9, we go over the internal wakes again of the metasurfaces, and then how to use them using the Ryan regulator, the Reynolds regulator. I always think of Ryan Reynolds when I see that for some reason. I don't know why, but it's going to be quite useful when applying this information to different aspects of technology. Section 10 goes over the applications. plasma stability, hydrodynamic predictions, the superfluid transitions, all this stuff is going to be useful for data transmission, I believe, and for power generation. So I have a whole nother thing on different uses for this, which I'll make a whole video for there as well. So in section 11 is the cosmological implications, how to read this information with our telescopes, what we're seeing. The infinity number, which is pretty much where an area saturates and everything kind of merges together or whatnot. Then we have the 6-dimensional Higgs anchor, which, like I was saying earlier, locks into the grain of space itself. Then we go into the grain persistence of macroscopic flattening. We got thermodynamic equilibrium and relativistic consistency. It shows how to interact with that. And it shows what it is, I should say. Section 12 is 12.2 is the weak equivalence principle. It shows that the inertial mass and the gravitational mass are identical. Section 12.3 is the Lorentz invariance and the dynamic lattice. They like to see their Lorentz invariances and transformations apparently at the scientific community. So it's important that we put that in there. Section 13 is theoretical robustness and falsifiability. It shows pretty much what we would need to see if you want to prove this information wrong. And it also shows some support for why we see what we do. It summed it up. It shows how to assess the baryonic averaging using the angle of attack for the generations of particles involved. It shows the origin of the strong force as well, the geometric confinement, and kind of goes down through what that is. Section 13.4, the metasurface link, topological coupling, axion-like coupling. That's going to probably be useful for information transfer as well. We go over the bridge equation that's closing the dimensional gap, kind of shows how they fit together with the hydrodynamic work, the scalar shear rate, the quantum shear rate, and then the Zitterberg frequency. They all play into matter and energy moving around. And then it goes into the geometric volume of all of those parts and shows why all that matters. Goes through the substitution and the equivalence, and it shows its thermodynamic validation there as well. Section 13, physical mechanism of duality, locked frames versus projected paths. Goes through a particle in a locked frame of reference because of its shape and size. The next part, it shows the wave, the projected path. Then the planetary spin down, just to make sure that we had these equations here correct. We kind of used it on Earth's orbital stability. So just numbers that we knew were right from experiment that we've seen time and time again. So we used that to show that these equations actually work. And yeah, it also explains that with lunar laser ranging constraint, it matches. So section 13.8 is distinguishing the vacuum expansion from dark matter. Section 13.9, limits and scaling relations. To strictly validate QSM as the origin of galactic dynamics, we must address three scaling relations that constrain the thermodynamic parameters: the Tully-Fisher relation, the reflective or excuse me, refractive index of the vacuum, the lensing, and the critical density threshold for anchoring. And then the next, it goes through all that. I didn't really want this video to be this long off the rip, but this is the first paper was kind of the longest paper. It has the baseline for the rest of it, so that way you have a solid understanding of what comes next. The conclusion kind of re-surmises everything that we just kind of discussed. So I take that back. That was just the first part of that paper. So we're going to go ahead and end this video now and take a break, and we'll pick it back up here in a bit. But thanks you for watching, and stay tuned.